Okay, welcome back to this second session of this afternoon, and our first speaker is Sebastian Jaimungal, who will talk about mean field games with differing beliefs for algorithmic trading.
Thank you, Martin, and thank you all for being here. Thank the organizers for organizing this great meeting for 10 years. I've been here not as often as Mateus, not every single year, but almost. I think I've missed 2 in the last 10 years. It's always a pleasure being here. So this is a talk on mean field games, differing beliefs, algorithmic trading. No direct link as well to Bruno's work, but hopefully I'll be able to throw in 1 or 2 things along the way. This is joint work together with my PhD student, Philip Casgrain, who's about to defend next week, in fact, when I get back to Toronto, the final defense for his thesis. And I think it's moving around too much. How's that? That's better, yeah, over here is. So Philip's about to defend next week, and he's worked on a number of problems related to algorithmic trading and incorporating mean field game type problems within this context. Before I start with the talk, I do want to remind those who know of, but maybe they haven't yet submitted their proposals for the SIAM conference. So as you know, as you may know, I'm the chair of the SIAM Financial Math group. And one of the duties of that chair is to run this conference and set it up, be one of the co-organizers. So it's happening in Toronto, June 4th to 7th in next year. And it's going to be on the campus of the university. It's the first time we're doing that. That's kind of an experiment for SIAM. They normally hold them at hotels. But this year we're doing this. We as well have a couple of new features. It's over 4 days, and on the first day, the afternoon session, we're going to have an industrial sequence of mini symposia. So there will only be 2 parallel mini symposia that have industrial focused speakers, as well as 2 panel discussions, one after another, one on fintech and artificial intelligence, and the other one on systemic risk. So it'll be quite different from previous SIAM conferences because of this. And there's also going to be a networking / reception session for the companies to try to recruit students and so on. So these are some new features. Yeah, Raphael.
When is the deadline to submit the paper?
Soon, December 5th, I believe. Yeah, so December 5th, yeah. So if you just Google, sorry?
December 5th.
3rd, oh gosh, okay. It's even sooner than I thought. I thought it was December 5th. Thanks, Stefan, for correcting me. Yeah, so please go Google SIAM FM19. The webpage will come up. Put in your submissions now. I think all you need for a contributed talk are your co-authors, yourself, and an abstract, titled abstract. Okay, so let's get on to my talk. And I should have started this 2 minutes ago. So background, this, as I said, this talk is on algorithmic trading, differing beliefs in mean field games. And algo trading has a lot of different topics that people cover within this context. The 2 that I'm going to focus on are optimal execution and statistical arbitrage, sort of a unified approach to both of those, where we also account for heterogeneous agents that have potentially different models that they believe the world evolves under, as well as different performance criteria, and there are latent factors that drive the market dynamics. So although you may believe that the market is moving, or you may only see prices, there may be other factors that are hidden to you that push prices in some direction, and you want to understand how do you trade in a context like that. So there's quite a bit of work on algo trading in general, but very little work on looking at latent factors as well as incorporating multiple agent settings. This is just a short list of, in fact, this is almost exhaustive of those that have worked in this particular area where you combine some of those. There's a paper that a postdoc of mine, Moshe Banorian, where we started this set of problems with mean field game strategy for optimal execution. And that's one of the initial papers in the area, and there's been several generalizations thereof. So before getting on, order flow is something that I want to discuss. Those who were here on the mini course saw a bit of this, so I'm going to go not super fast, but a little fast. So trade and volume and intensity, as you know. Trade volume through the day is stochastic. It fluctuates. This clearly also affects prices, and we want to understand how that order flow information can be used in terms of predicting prices and in terms of writing down price dynamics. So here were 2 empirical facts that we saw from that mini course. One is that price impact from trading over short time horizons and looking at order flow is positively correlated to price changes. And if you look at that price, that permanent price impact over these short times, then that permanent price impact is approximately linear. If you look at sending orders immediately and executing them and walking through the book, it's not linear. There's some concavity in there, but we're going to approximate that as a linear function to avoid, to be able to obtain analytical solutions. There are ways to generalize these in which you'll end up with similar kinds of systems of equations that we have, but we can't solve them analytically. So with those two bits of empirical facts that we saw covered in the mini course, there's these are the two basic models that we're going to use for the single agent player. So the first object up there, S hat, that represents the price that you receive by selling, when you sell shares or pay. So new positive is your rate of trading. If you're buying, you're going to be charged not the mid price, but the mid price plus this correction, which is linear in your rate of trading. As well, when you buy, and when all agents buy, there's this extra drift here in the asset price. So M is a martingale, and that drift accounts for the fact that you look at the total order flow of all agents. So mu plus are all buy orders, nu are your orders, mu minus are other agents' sell orders. So that drift, those two pieces, those two linear pieces that you see there, are reflected in this empirical picture here. Okay, so given that you trade at a particular rate, how much cash do you have over the time horizon? Your cash process is given in the equation at the bottom. You can clearly see it's composed of the mid price plus that immediate execution cost, and then you multiply by the number of shares that you've traded over that short instant of time. So if you accumulate this cash through time, you now want to ask a question. Now the agent will ask a question, what control problem do they solve? For the single agent, we're going to look at this control problem. So you take the terminal cash that you receive from trading throughout the entire time horizon. You may have shares at the end, Q, and those shares are going to be valued at the mid price. So we're going to, you can see here this terminal book value here. That's the share price at the end. That's the amount of inventory you hold. But we're going to penalize holding inventory by this quadratic term. And in addition, there's this other penalty that shows up here, which is the integral of the squared inventory through time. This is a running inventory penalty. You can think of that running inventory penalty as an urgency parameter. So if you don't want to hold inventory throughout time, make that large. And that will force you to get rid of inventory earlier on. You can also interpret it, there's a nice paper by a former PhD student of mine, Ryan Donnelly and Alvaro Cartea, where we demonstrate that this problem is equivalent to a sort of a robust optimal control problem, where what you do is you say, this is my base model, however, I'm not sure about that drift. In particular, we're going to look at a set of equivalent, we're going to take a reference model here, we're going to look at a whole bunch of potential candidate models which are equivalent in probability, so or I should say absolutely continuous. We're not going to consider models which are not absolutely continuous, but even within that set, because we can have jumps and so on, there's a lot of non-trivial behavior there. If you look at these other candidate models and you say the universe may throw that at you, so in other words, the universe hurts you, which is why you take an IMPA over all of those other candidate models, but you're going to penalize those candidate models via relative entropy. So if they're too far away from your reference model, you think that that's really ridiculous. It can't possibly be. Instead, only models that are somehow within some ball around you are relevant. And how relevant and how big that ball is effectively is controlled by this parameter phi. If phi goes to 0, then you're really, really confident of your model. Anything that's different from your reference model would get infinite penalty. And if phi is small, then all models are just as equally valid. So that problem turns out to be, when you solve it, equivalent to this problem. That's quite an interesting result. Now, when you solve this particular control problem and you find the probability measure that attains the minima here and the corresponding control, and you go back and ask yourself, what is the measure that the agent is behaving as if the world is evolving according to? It turns out that that probability, or that probability measure, implies that the asset price is what you thought it was, except there's an extra drift, and that drift correction is negative this ambiguity parameter, this phi, times the inventory you have. So if you have a long inventory, you trade as if you believe the world is going to have an extra negative drift. If you have short inventory, you trade as if the world has an excess positive drift. In other words, you trade as if the world is going to work against you. But the amount that it works against you depends on the ambiguity that you have. Okay, so that's quite a nice little result. So I'm not going to go through the solution of this optimal control problem. I'm just going to tell it to you because I want to move to the multi-agent setting and where all of the new interesting features are. So the optimal solution has this form, and I'm actually going to write that form on the board so that we can remember it. It has the form. Where did the chalk go? Okay, here. The optimal trading rate looks like nu star is equal to some function of time minus some other function of time times your current inventory. Okay, it has that form. And these two, this function of time is deterministic, while this G1 is a stochastic process, and it's given by the integral from now into the future of some function, expectation of excess drift, conditional on the information you have at this point in time. Now, this is a model agnostic result in the sense that the particular model that you have for order flow is irrelevant. Any model for order flow that you choose to write down, this will be the optimal solution. And in particular, we saw some examples in the mini course where that order flow can be thought of as coming from some machine learning model. There might be some latent factors there. There might be other factors other than order flow itself that feeds into things. But nonetheless, this order flow ends up correcting the baseline strategy, which is the Almgren-Chris strategy here, by a term that depends on the average expected order flow all the way into the future from now, given what you know now. Keep that picture in mind. The multi-agent problem is going to have something similar, which is what's quite interesting. Okay, so let's go to the finite player multi-agent game, and then we're going to eventually go to a mean field version of it. So we're going to think of the situation where we have n agents, but they're of distinct types. So there might be, say, 3 different types of agents here. We have the agents on the left side of the room, we have the agents on the right side of the room, and we have the agents right up at the front here. And perhaps these agents have different models in mind. They may have different performance criteria in mind. Some of them may be agents who want to execute trades. They have a large position and they want to get rid of it. Some of them may be agents who are just simply performing statistical arbitrage and trying to make money off of things like mean reverting prices. And then there might be some other agents who are kind of a combination of those two. And again, they may have different particular beliefs about the model that they're going to use in addition to what it is that they're trying to do. We're trading on a fixed time horizon, as it says there. So what's the setup? It's going to look similar to the single agent game. By the way, this is not a caipirinha. Okay? It's just watermelon juice. So it looks similar to the single agent game, except we have to keep track now of all trading rates. So nu is now a vector of trading rates for every single agent. So although we have different subpopulation types, we need to keep track of every single agent. In addition, we're going to keep track of their corresponding inventory, which will be denoted by Q with the superscript J, and the new J there just reminds us that it's controlled by their trading rate. As well, each agent, we are going to keep track of what their cache process is, just like in the single agent problem. However, now we have this cache process which depends on this parameter AK, which varies across subpopulations. So it could be that certain subpopulations are very good at reducing their temporary impact, while others are not so good at doing it. Okay, so we have a dependence on the subpopulation there. This is one way in which populations are different. The next way, the other bit that we need to really think about in the multi-agent game is what information set do the agents have access to? What filtration is their strategy adapted to? So before talking about that part, let's just go here to the dynamics of the asset price. So this asset price model looks similar to the one that we had for the single agent problem. There's a martingale component there. There's a stochastic drift, which was before the difference between positive order flow and negative order flow. And there's now the action of all agents here. So we are taking into account the total order flow of every single agent. Now notice that the M and the A have superscripts K on them. That means that different agents and different subpopulations have a different model in mind. Okay. M is a martingale under probability measure. MK is a martingale under probability measure PK. That's the way that we can distinguish the different models. Now, agents do not have access to AK or to MK separately, even if they're within a particular subpopulation. What they do see is the price, S. So the filtration that they're going to adapt their trading strategies to is S. They will also adapt their strategy, of course, to their own inventory, because it's something that they know and they are controlling. They will also adapt their strategy to the total order flow, but they cannot distinguish individual agents' order flow. And that's important. In the finite player game, because of this information asymmetry, you can think of it as an asymmetric information problem or partial information problem for a multitude of reasons. One, we don't have information about every single individual agent, and agents cannot see each other. And two, the stochastic, the martingale component here and the corresponding, the drift component are not visible. They're not part of the agent's filtration. So there's a large filtration here, G. Each agent is going to adapt their strategy to a smaller filtration, FJ, and it's the one that I just described. Okay? Can I answer any question about this setup? Because it's important to make sure you have this in mind. We're all good? Great. So what is the performance criteria of each individual agent now? What we're going to write down for the performance criteria is we're taking an expectation under their probability measure, so for their subpopulation, because everyone in their subpopulation has that model in mind. And we simply add up exactly the same three types of terms that we had before. So there's a total cash, there's a liquidation cost, and then there's a running penalty. However, we already noticed that the dynamics of, the execution price for an individual agent depends on their subpopulation. So that's why AK varies across subpopulation. They may also have different terminal penalties. Maybe some agents want to hold inventory overnight. So this could be 0. And some agents don't want any inventory. So this will go to 0. Sorry, go to infinity. And they may have different urgencies. Or, as we saw for the single agent case, we can interpret it as the agents having different model uncertainty or model ambiguity. All agents trading affect every single other agent through the dynamics of the mid-price. So there's this highlighted yellow that you see there, which is both the probability measure as well as the agent, as well as all of agents' trading speed. So our goal is to find a Nash Equilibria for this problem. We want to be able to find the optimal trading strategy that every agent should follow, such that if any one of them unilaterally deviates from that, they will underperform. They will have a lower value function. If we can find such a point, that'll be our Nash Equilibria. We cannot do it in the finite population case. Instead, we're going to take the infinite population case, take everyone going to the number of agents going to infinity in a particular way, and hope that we can find a Nash Equilibria for this infinite population problem, and then take a version of that infinite population problem and apply it to the finite agent case. And hopefully, we can show that that finite agent or that infinite population solution applied to the finite agent case is close to a Nash Equilibria. That's our goal. So the way that we do this is we're going to take the infinite population limit by keeping the proportion of agents within each subpopulation fixed. So that's the first thing. This is not necessary, right? We don't have to do that to find an infinite player game. However, it's unclear, if we don't know yet, how not to do that and obtain an infinite player game that says something about the finite player game. For us, it seemed to be the simplest way to do it is to keep the subpopulation ratios fixed as we take the population up to infinity. In that case, the effective dynamics of the mid-price process now gets, and one other thing, we are going to write down a mean field strategy for agents within the different subpopulations. So nu bar K is going to represent the average of everyone's trading rate within this subpopulation. That would be nu 1K, nu 2K, and nu 3K as we take these populations to infinity. So given that stochastic process, and it's a stochastic process, not a deterministic function, right? Some stochastic process, That's what we'll call the group mean field. In that case, the dynamics of the mid price now becomes this effective dynamics where we have the mean field speeds or mean field trading rates showing up in the SDE for S bar. And the important part of this is that the mean field is unaffected by any one epsilon agent from deviating from whatever strategy they chose. What we show is that, in fact, this mean field strategy turns out to be adapted not just to the filtration generated by agents within one subpopulation, but it's actually adapted to the filtration generated by every agent. So in other words, it's the intersection of all of these, all of the filtrations that we have around, which is kind of a nice, makes things a bit easier. It turns out that that's a result, that's not an assumption. So in order for us to solve this problem, we want to do one more thing. Remember, there's partial information here, even in this infinite player game, because the agents do not know what AK are, nor do they know what MK are. Those are hidden. We still only observe S, but now this mean field S. So to do that, to solve that issue, we use a projection-like result. So you can prove that there exists a process A hat K, which is the expectation of A given the filtration that you're adapting to. And there exists some martingale M hat K, and those are adapted to this filtration F. With those particular stochastic processes, you can rewrite the price in terms of these new stochastic processes. And that means that you can rewrite the price in terms of stochastic processes that are actually adapted to this reduced filtration. It's quite a nice little projection result. Once you do that, you now go back to the control problem that the agent aims to solve, and that control problem has this form now. If you finagle it a little bit, you end up with this form that looks like a quadratic form in the rate of trading and inventory, as well as this extra stochastic integral here, because S is a stochastic process still, and that stochastic integral depends on the mean field trading rates. This is not exactly a linear quadratic programming problem, although the argument of the integral and the terminal penalty there is linear quadratic. It's not linear quadratic because of the stochasticity that feeds into S. If S was deterministic, then you can just use classical linear quadratic programming problem solutions. So now what we want to do is, given that the performance criteria can be rewritten in this form, we're going to seek for the optimal strategy of every agent in a way that's self-consistent. So the self-consistency is, remember, we have a mean field for this population, this one, and this one. And that's in the limit. We're going to take an arbitrary agent from within a particular subpopulation, find the optimal control for this individual, find the optimal trading rate. Then we're going to average over all of the agents within that subpopulation. That had better be equal to the mean field. This is the mean field consistency criteria. So hopefully we can solve that problem. Turns out this can be solved because this is a convex optimization problem. And if you were attended Temu's talk, you can see that there are some techniques, lots of techniques in convex optimization that one can use. So I'm not going to use dynamic programming and generate forward Fokker-Planck equations. I'm not going to use the stochastic Montriagan maximum principle to get a system of FBSDs, which you then go ahead and solve for the optimal control. Instead, I'm directly going to use optimization techniques from looking at the fact that this is a convex functional on the space of strategies. So to do that, what we first show is that H bar, in fact, is strictly concave. Secondly, it is everywhere Gateau differentiable. So that means if you take an arbitrary point in the control space, take some arbitrary direction that you want to move in, and compute the derivative there, it exists for every single point in your space of optimal strategies, and it's explicitly given by that. Don't worry about the expression. It doesn't matter. What we next show is that, indeed, the necessary and sufficient condition for us to find the optimal position is to ensure that this vanishes everywhere for every omega. We need to find the point such that this vanishes for every omega. And we can show that that is equivalent to solving this infinite dimensional system of FBSDEs. So these are forward-backward stochastic differential equations where each M here is a martingale under the measure induced by the subpopulation that that agent is from. And the mean field for that subpopulation, and this is sort of a vectorized version of things, shows up there, as well as this stochastic drift. And there's some terminal condition there. And we want of course, to ensure this self-consistency condition. Now you might say, okay, that's great. We now have an existence. By the way, we know that there exists a solution to this, and it's unique because the original stochastic optimization problem, which it comes from, is strictly concave. So it has to be. So even if we couldn't solve that, we know that the solution exists and is unique. However, we can explicitly solve it. The idea is that what we're going to do is take the fact that there's sort of a one-way dependence here. There's a certain type of one-way dependence. We can average over agents within a particular subpopulation, then get a vector finite dimensional system of FBSDEs for nu bar, and that we can solve. Then we can plug back in and find the individual agent. So here's the structure. This is what I want to get to. The structure for nu bar is that 1 over A minus, that's some A minus, A inverse is the temporary impact matrix for all of the different subpopulations. And then there's this G1 of T plus G2 Q bar. Look at what's on the board. It's of exactly that structure, except now we have a vector which represents the subpopulation mean fields. What shows up in G1 is a stochastic process, and that stochastic process depends on the future expected drift, filtered drift. So A hat is the one that you filter onto the information set that you have. But the discount the sort of discount factor, the L that showed up over there, are stochastic processes themselves. And those discount factors are related to the Radon-Nikodine derivative, which connects you from one probability model to the other for the different agents. It's a matrix collection of them. And then the individual agent, the way that they trade is given by this formula. So if you look at this, look at the very right term of that expression. An agent within subpopulation K trades at a rate given by its subpopulation mean field. The first term corrects that. The correction is given by the deviation between their inventory from the mean field inventory times some function of time. And there's a negative sign in front of that. So this means if my current inventory is higher than the inventory for my subpopulation, the term number 1 there is negative. So I slow down. And the reason I slow down is that I'm trying to get to the subpopulation's rate of trading effectively. I'm trying to match it. If Qi equals Q bar, I ended up with 0. I end up with just trading at the mean field rate. Okay, so that's quite an interesting result because we started up with this multi-agent control problem, multi-agent stochastic game, where there was nowhere where we specify there's a penalty for not trading along with the crowd, quote unquote. There are many examples of mean field games where that's an output of the result. However, it's also usually an input in the sense that you explicitly penalize the deviation from the mean field as part of the specification of the performance criteria. And so it's not surprising that it comes out. Here, that's not specified a priori, yet it comes out, which I find quite fascinating. Okay, so then you might ask, well, does this, in fact, give us a mean field solution? An epsilon Nash Equilibria for the finite player game? Indeed, it does. So what that means is you can improve if you deviate from the strategy, but only by an amount epsilon. And epsilon goes to 0 as n goes to infinity. So it's a very nice proof. Here's a simple example. I know that, we have a little bit of time, so I'll do this example. Here's an example which, again, we saw in the mini course, where we take a price process in which the underlying dynamics is a mean reverting pure jump process where you don't know the level that it mean reverts to. Okay, so there's an underlying latent process that drives the mean reversion level. The real world is switching between those. You don't know what it is. All you observe is price. Let's see how these agents interact. So here we did the example, with 2 subpopulation types. So there's the blue guys and the red guys. So the blue, they are execution agents. They have, on average, a positive inventory to start with, although their inventory is not all the same. So this axis is inventory. They have a spread in inventory, but on average, they're positive. And they're trying to get rid of shares. They're trying to get down to 0, and they have some urgency in doing that. So you can see that, on average, all of those guys go down to 0. But there are some fluctuations there in which they're trying to adapt their strategy to the stochastic drift that they see or that they've filtered. The red individuals on average have an inventory of 0, and they are statistical arbitragers. So they are trying to take advantage of the fact that they're filtering what that drift is and which level you're mean reverting to and doing stat arb. But both of these subpopulations are doing this not in isolation, but accounting for the fact that the others exist, which most papers in algorithmic trading completely ignore. There's some extra detail there in terms of what's happening with the prior probability measure. So here you can see population blue believes that the price is going to mean revert up initially, and red that it's going to mean revert down, and then they eventually converge because they're all looking at the same price. Okay, so I think I'm going to just stop there and leave a couple of minutes for questions, except I'll just say, happy birthday, Bruno. Jan.
So, according to Brazilian rules,
Yeah.
questions are at the end.
Ah, okay.
So, we move to the second speaker.
I think I